Hi there, Year 12. So this is the lesson which I'm going to be teaching to the other group on Tuesday. So I hope that you're okay with me doing this video for you for Monday. That way, by Wednesday, we're all at the same point. And what I want to talk about today is how we use differentiation. What's the point? We've talked about it in a very abstract way. Equations of normals and tangents and finding turning points and working out when functions are increasing or decreasing, but how do we actually use that in the real world? So I want to talk about two things today. Firstly, rates of change. So if you picture a balloon, okay, and you blow the balloon up, and these balloons are generally spherical-ish, aren't they? A bit elliptical maybe. But as the radius of the balloon increases, the volume is going to look something like this, isn't it? It's not a straight line because a doubling of the radius would make the volume 2 times 2 times 2 8 times bigger. So it looks something like that. And the gradient of that graph at any point is the rate at which the volume is changing. Now we need to be careful because for this graph it would be the way that the volume is changing in relation to the radius. So we would call it the rate of change of volume with respect to the radius. We could draw a different graph showing time, and we might be blowing this balloon up at a constant rate, and it would probably therefore look something similar. But the gradient of that graph would be the rate of change of volume with respect to time. So anyway, this is one application of differentiation, finding rates of change. So let's look at an example, which is the volume of an expanding sphere. So maybe this is a balloon, I don't know. But we know the formula for the volume of a sphere. It's the 4/3 pi r cubed. By the way, this is on a handout that I've attached. So that is going to give me something like this. I mean, I could plot it exactly and get an idea. Obviously, the graph would be defined for negative values of r, but the radius of a balloon or any sphere has to be greater than or equal to 0, doesn't it? So we're only looking in this quadrant. So if I differentiate this, what I get is not dy by dx, but dv by dr. And that is the rate of change of volume with respect to radius. So that's how fast the volume is increasing in relation to the radius. So let me differentiate this. I've got a funny coefficient here, 4/3 of pi, but I'm going to multiply by the power. If I multiply 4/3 by 3, I get 4. So I get 4 pi and reduce the power by 1. R is the variable, isn't it, in this expression? 4/3 pi is a constant, that's the coefficient. So I get that. Now, of course, the gradient isn't constant, it's changing. Different value of R gives you a different gradient. So what do I need? What value of R do I need? Well, I've got to find the rate of change when R is 5. So when R is 5, dV by dr is equal to 4 pi times 25, which is 100 pi. Now, what are the units of this thing? Well, it depends on what the volume is being measured in. So it's centimetre cubes per centimetre. And what that means is, at the instant the radius is 5, every 1 centimetre increase in radius is making the volume 100 pi bigger. Of course, it only works at that instant, so it's a slightly confusing definition, because by the time you get to a radius of 6, this would be much bigger, because it would be 4 pi times 36. But that's what it's telling us. It's the rate at which the volume is changing at that instant. Okay, so two fairly straightforward questions for you to try along those lines. In both cases, you're given a formula for something, area and displacement, that's distance effectively, isn't it? And you are asked to differentiate it to find a rate at a particular radius or a particular time. see if you can pause and have a go at those two questions. So with number 4, that's the area, the surface area. I differentiate it so I get dA by dr. R is my variable. So I multiply by the power, so 2 times 4 pi is 8 pi, reduce the power by 1. So that's dA by dr, and when r is 6, I get 48 pi centimetre squares per centimetre. So every 1 centimetre increase makes the area 48 pi centimetre squares bigger at that instant. It's varying though. And here we've got displacement or distance equals this formula involving time. So when we differentiate it, we get ds by dt, 2t plus 8, substitute that in, and that's going to be meters per second. So yeah, the rate of change of displacement with respect to time, that's speed, isn't it? And rates of change nearly always involve dt, because we're talking about how fast something is changing with respect to time. You do get these ones where it's with respect to the radius, but the ones we're most interested in are ones where it's to do with dt, because that's the rate at which something is changing with respect to time. Okay, a harder example now in this next question. So we've got the total surface area of a cylinder has a fixed volume. Okay, so the volume, however we fiddle with the dimensions, has to be 1,000 centimetre cubes. Perhaps it's being designed to hold a litre, so that's why it has to be fixed. And in this question, we are being asked to demonstrate that therefore the formula for the area of that cylinder is this, where x is the radius. So what I would start to do is I would say, okay, here's a cylinder. Now that cylinder can be described with only 2 dimensions really. I've got h and I've got the radius, and I think we are using radius as x, aren't we, here? Those are the only 2 dimensions I need to describe that. Although, of course, there's no mention of h here. So the first thing I'm going to do is I'm going to write a formula for the volume of that cylinder, which I know equals 1,000. And that should allow me to get a formula for h in terms of x. That's my first step. So can I invite you to have a go at that? Write a formula for the volume and rearrange that to get a formula for h in terms of x. First step, pause and have a go. So hopefully you remembered the volume of a cylinder, area of the base multiplied by the height. So the height is the volume divided by pi x squared. So if the volume is going to stay the same, if we make x bigger, the height has to get smaller. So we've got, a sort of 2 interconnected variables here if the volume is going to be fixed. Right, let's now consider surface area. What I now want you to do is to write me a formula for surface area. And you may remember that the surface area of a cylinder is fiddly, isn't it? You've got your 2 circular bits, and we know we've got the radius of that, so those circles are x. But then you've got the curved surface area, which is, that's your sort of your label, your bean tin label. And you've got to remember what the dimensions of that are. So if I take that curved surface area and sort of stretch it out, I get a rectangle. But working out those 2 dimensions is, it's a little fiddly. So see if you can write me a formula for surface area. That's going to involve x and h, but then see if you can replace h with this. This is what we're aiming for. We're hoping we're going to get to there, okay? So see if you can get somewhere along that road. I'll come back in a minute with my solution. Okay, so the area of the 2 circular ends, top and bottom, pi x squared. Do you remember the bean tin label? Well, obviously its height is h, but its length is the circumference of the circle, which is pi times the diameter, so that's pi times 2 x's. So when I work out the total surface area, I've got 2 lots of pi xh, 2 lots of pi x squared, which is happy days. And then I've got this multiplied by this, the area of that label. Now, you know, it doesn't really matter what order we write it in, but I've sort of followed the pattern they've done. So I've written that as 2 pi xh. That's just that multiplied by that. Okay, so I'm now going to replace h with what we derived it as here. Okay, so the surface area, they're using a, actually, not surface area, they're using just a. So that's 2 pi x squared plus 2 pi x. H is this, so I'm going to replace h with so this is one fraction effectively, so I'm going to, you know, and that's good news, isn't it? Because I've got the pi's cancel out. I've got x and x squared, so that's going to cancel out one of those x's, and I've got 2 times 1,000, which is 2,000. So I end up with 2 pi x squared plus 2,000 over x. Bingo. So I've derived the formula for the surface area in this particularly, you know, convoluted situation where you've got a cylinder with a fixed volume. Okay, we're now got to show that the rate of change of area with respect to the radius is 0 when x cubed equals this. So rate of change of area with respect to the radius, well, that means we're going to differentiate this to get dA by dx. I'm going to rewrite it first in index form. Go on, see if you can differentiate that, and then see if you can prove what they are after. I'm going to get some more paper because I'm running out of space. Okay, so differentiating, multiply by the power, reduce the power by 1, multiply by the power, reduce the power by 1, and remember that means that. I think most people seem pretty comfortable with that now. But this question is different, isn't it? It says, show that when the rate of change of area with respect to the radius is 0. So we're not being given a value of x, we're being asked when is the gradient, when is the rate of change 0. This is a turning point, isn't it? So we've got to ask when does it equal 0, and you know, we're used to this with y's and x's, so it's a very similar process, and we're given the answer. We've got to show that x cubed is 500 over pi, and hopefully you can see that you get there in some form. You didn't have to divide by 4 at that point, you could have done it later, but we get there eventually. So the rate of change when x is this value is 500 over pi. So this is a turning point. So I'm going to go back and have a little look at what the graph of the area looks like. I'm going to plot that on my calculator. Now it's not an easy graph to plot. If you plot this just in standard mode, it looks really, really odd. But if you fiddle with the axes, so I've gone from sort of effectively in the x direction 0 to 30. I started at -1 just so I could actually see the axis. And the y-axis I've gone effectively from 0 up to 10,000. You can see you get a minimum value for the surface area. So this is us increasing the radius. And remember, if we increase the radius, if the volume's going to stay the same, the height's going to get smaller. So what we're finding here is as we increase the radius, the surface area that we need to make this cylinder drops to a minimum point around about here. And I haven't scaled this axis, but it's, you know, it's sort of single digits of x somewhere. Well, in fact, it's the cube root of 500 over pi. And then it goes up again. Now, you know, why is this relevant? Well, if you are the manufacturer trying to make your cylinder, which has a volume of 1,000, which seems to me to be almost certainly something that would hold a litre, 1,000 centimetre cubes holds 1,000 millilitres, then why are you interested in a minimum surface area? Well, it's because that is your optimum solution, isn't it? This is the size of cylinder which is going to need, this is surface area, remember, it's going to need the least material to make it. If you're making it, if it's a tin, made out of metal, then this is the minimum amount of metal you're going to need. So you want to design your container, your cylinder, so that you've got a radius around here, so you're using as little material as possible. That's going to be cheaper for you, isn't it? So this is using differentiation to optimize a problem, and that's the second main application of differentiation in the real world. So yes, differentiation to find optimum solutions, both maximums and minimums. So in that last example, we were looking at the surface area we needed to give us a cylinder with a volume of 1,000 centimetre cubes. We were interested in the minimum because we wanted to do it with as little metal as possible. Here we've got the reverse problem. So we have a fixed amount of metal, 54 metre squares of metal. And we want to make a tank from that. The tank has an open top and two opposite faces are square. So you've basically got a square end here and a square end here, and then the sides here. And you've got 5 faces. You've got the 2 square ends, and then you've got a side and a base. Let me draw in that. No lid. And those 5 faces, you've got 54 metre squares at your disposal to make them. Okay, so let's put in some dimensions. We are told about this value x, which is the height of the tank. Now, if the ends are square, then that means that the width of the tank, or whatever you want to call that dimension, is also x. And so the only other dimension is length. So go on, start off by seeing if you can get a formula for L. This time we want to do it by firstly writing a formula for surface area, because we know the surface area is 54. So add up all of your faces, there's 5 of them, add up the area of those 5 faces, make it equal to 54, and then see if you can rearrange that to get an L equals formula. Okay, so I've done this the long way just in case you're not clear on what I'm doing. So the surface area, and don't forget we haven't got a lid, so you've got the end, which is x squared, another end, x squared, you've got the base, which is x times L, and then hopefully you can see the sides are also x times L as well. So that's my surface area. And no mention of L here, so just like we did in the previous question where we did it the other way around, we started with volume. We're going to try and get a formula for L, which I've done. You could have done that in one go, but there's a reason why I've left that. It'll become clear in a minute. And although when I divided by x here, I chose to divide everything by x, you could have just written it as that all over x. And remember, this and this mean the same thing. So it doesn't actually matter whether you write it like that or whether you write it like that. The important thing is that when you divided by x, one of the x's there disappears. Okay, so the volume of this box is the 3 dimensions multiplied together, x times L. Now you might say, well, hang on, you're patronising us here. We know that's x squared L, but forgive me, can you see why I left it at that point? Because all I want to do to work out the volume is take XL and multiply it by x. So actually I don't need to use this version of L. I can just say, okay, the volume is x squared times L, which is x times XL. So the volume is that multiplied by x. And I've written it like that because that's the way they've written it, but remember that's the same as this. It means the same thing. So these two things are the same. Okay, so we've got a formula for volume, and it's with respect to the size of x. Remember, this time the surface area is fixed. So if you make x bigger, L is going to have to get smaller because you've only got so much metal to make. So now let's see if we can find the maximum volume that we can get using this particular situation. So can I invite you to find dv by dx and ask, when does it equal 0? That's the turning point that we're after. Have a go. So dv by dx is 18, 3 times 2/3 is 2, so minus 2x squared, and we're looking for a turning point, so when does that equal 0? So I divide it by 2, and then you could go two ways. You could just do it this way, or I multiplied everything by minus 1 and just spotted that was a difference of 2 squares. Anyway, we get the same answer. There's a turning point in the size of the volume, don't know whether it's maximum or minimum yet, when x is minus 3 or x is plus 3. Now x is the radius, x is the length of the end or the height of this box, so it can't be negative, can it? Can't be negative. So we know we're dealing with plus 3 as our turning point, but is that a maximum volume or is that a minimum volume? In fact, we're asked to justify whether we found a maximum or minimum value, so we know how to do that. I mean, common sense tells us that it's going to be a maximum, but let's prove it. So we've got dv by dx, so let's differentiate that again. And let's substitute in the value of x at our turning point, and let's work out whether it's a maximum or a minimum. Go for it. Okay, so I have differentiated again. So this was dv by dx, so dtv by dx, which is just minus 4x. When x is 3, that's negative, so we know we're dealing with a maximum. So what is the maximum volume? Well, I can see from I plotted the graph again. I had to massage the axes a bit, but yeah, I've clearly, as you increase the value of x from 0, this is 1, 2, 3, 4, so it's just after 5, you get a maximum volume somewhere below 50, and that's a bit like working out the y value when you know the x value of a turning point. So where do I go? Well, I go back to my original function. So when x equals 3, v equals, so I've got to substitute 3 into that original function. I've been encouraging you to use your calculator for that, and there's a neat little trick you can use actually. I've already typed this function into the graph section, and if you go to menu and table, it's got the same functions that you've typed in. So the table function, the graph function use the same functions. So if I just go to set and say, right, I only want to work out the value when x is 3, so I'll just use 3 as the only value I use, and go to table, it gives me the answer. Now I could do it using the normal calculator method I've shown you, but yeah, volume is 36. If you substitute 3 into this, volume is 36, and don't forget the units. We're dealing, I think, with meters in this question. Yes, so that's 36 meter cubes. So if we only have 54 meter squares of metal and we want to make this box, then our optimum solution, the dimensions that give us the maximum volume, are to have ends that are 3 meter by 3 meter squares. There we go. Okay, so I'm conscious that the video is probably long enough already, so I had got a number of practice questions based on this, but we'll just do one. Well, in fact, sorry, I'll get you to do one. This will be a submission question. This is a simpler version than the ones we'll be doing because it's only in 2 dimensions. You've got a constraint, which is a length of fence. You've got to show that using that length of fence, this is the area of garden that you get, and you've got to differentiate it to find the maximum possible area that will give you. So have a go at that. The good news about all 3 of the last 2 questions we've done and this one is that they always give you this formula. So part A is show that A is this or V is this or whatever, but they give you that formula. So even if you can't do part A, you can still do part B, because even if you completely fail to get that, you can differentiate it, dA by dy, and carry on. So yeah, they're sort of helping you out there. And don't forget, with this one, before you try and differentiate anything, you need to multiply out that bracket to get 80y minus 2y squared. Okay, I look forward to seeing you in school on Wednesday. How exciting.